Part 3 of this playlist is devoted to the directed integral. We want to integrate multivector valued functions on manifolds. The directed integral does this. It generalizes line and flux integrals from vector calculus. Let's see how to generalize a line integral to a directed integral. Here we have a line integral. It's an integral over a curve in Rn. This is a vector-valued function on the curve, and this is an infinitesimal vector tangent to the curve, and I take their inner product. Here is what the generalization to a directed integral looks like. It's still an integral over a curve. ds is the same as before, but now f is a general multivector valued function on the curve, and this ds times f is then a geometric product. I want to look at this infinitesimal vector tangent to the curve a little bit. It's in the tangent vector space to the curve, a one-dimensional vector space. And of course, that one-dimensional vector space R1 extends to the geometric algebra G1. The tangent algebra to the curve. In G1, the one vectors, that is to say vectors, are the pseudoscalars. So this infinitesimal vector can also be thought of as an infinitesimal pseudoscalar in the tangent algebra to C. Next, we'll generalize flux integrals to directed integrals. So here we have a flux integral. It's an integral over some surface in R3. F is a vector-valued function defined on the surface, and d sigma is an infinitesimal vector normal to the surface. This works only in R3 because only in R3 do two-dimensional surfaces have unique directions normal to them at each point. The generalization of a flux integral is then this. Here's the directed integral. It's still an integral over the surface, but ds here is an infinitesimal bivector in the tangent algebra to S. F is a general multivector valued function on the surface, and we have, again, a geometric product. Now, this works then in all dimensions, and I want to look at this infinitesimal bivector a little bit more. It's in the tangent algebra G2. Its pseudoscalars are therefore grade 2 multivectors, that is to say, bivectors. And so another way to look at this infinitesimal bivector is that it's an infinitesimal pseudoscalar in the tangent algebra G2. And this works in all dimensions. We're now ready to discuss directed integrals over arbitrary manifolds. Recall that our goal is to integrate multivector valued functions on manifolds, and the directed integral, does this. Actually, I think it's pretty clear how to proceed from our examples, especially the example of the generalization of a flux integral to a directed integral. The hard part is devising a suitable notation to express directed integrals in manifolds of arbitrary dimension. So let's look at the notation we've used so far for our directed integrals. In the new notation, those directed integrals look like this. ds is replaced by d1 of x. The 1 tells us that we're integrating over a one-dimensional manifold, that is to say, a curve. The 1 also then tells us that this d1 of x is a pseudoscalar of grade 1, that is to say, a vector. Here, the d2 of x replaces ds. The 2 tells us that we're integrating over a two-dimensional manifold, that is to say, a surface. The 2 tells us that this infinitesimal is an infinitesimal bivector in the tangent algebra to the surface S. Here then is a general notation for a directed integral over an arbitrary manifold M. The manifold is of dimension M. This is then a pseudoscalar of grade M. It's an infinitesimal pseudoscalar in the tangent algebra to the manifold M.